Hello everybody, we're going to try a related rates problem today. This one has to do with a cylinder. So we're saying the radius of a cylinder is going to be increasing at a rate of 2 centimeters per second. We're claiming the volume is increasing at a rate of 6 pi centimeters cubed per second. And we're wanting to know how fast the height of the cylinder is changing when the radius is 3 centimeters and the height is 5 centimeters. So we'll notice that every quantity in this problem has to do with either the height, the radius, or the volume of the cylinder, or the rates of change of those quantities. So we're going to want to start with this equation, the volume of a cylinder. Now this equation isn't quite adequate for us because some of our quantities that we're working with are rates of change, and this equation does not deal in rates of change. And so we need calculus. What we need to realize is that the quantities h, r, and v are all functions of time. They all change as time goes by. So what we're going to do is we're going to take the derivative of both sides of this equation with respect to time, and it's going to create a new equation that we can use. So the derivative of the left-hand side is the derivative of v, which is dv dt, the derivative of v with respect to time. The derivative of the right-hand side, well, we have to realize that pi is constant, and that's fine. And r squared and h are both functions of time. And so if we're taking the derivative of a product of functions, we need the product rule. So this is first function, r squared, times the derivative of the second, plus the second function, h, times the derivative of the first. So there we go. And so when we take these derivatives, we now have this new equation that's going to be useful to us because this equation has these rates of change in it, and this is going to be helpful. So all right, we have all of this information up here that we can just put into the equation. So let's go ahead and give it a try. dv dt, the rate of change of volume. So we look up here and we see the rate of change of volume is going to be 6 pi centimeters cubed per second. So we'll just go ahead and we'll put 6 pi in here. Next up, we'll just leave the pi where it is. And we need to know r squared. What's the radius squared? Well, at this instant in time that we care about, the radius is going to be 3 centimeters. So 3 squared is going to be 9. dh dt, we don't really have dh dt up here, but we're being asked how fast is the height of the cylinder changing. That's directly asking us for the rate of change of h. And so dh dt is going to give us the answer to our problem. So we won't know it yet, but we will soon. So leave dh dt right there. We know what h is. H is going to be 5. And then times 2 times r, which we said was 3. And then times dr dt, the rate of change of r. And we said the rate of change of r is 2. So there we go. This is exactly what we need. And so we know that 6 pi is equal to pi times 9 dh dt plus 5 times 2 is 10, and 3 times 2 is 6, so this is 60. There we go. So this is pretty good. Let's go ahead and divide out by pi. And what we're going to do is we're just trying to get this dh dt by itself. We're trying to solve for dh dt. So we're going to subtract 60 from both sides. And after we've subtracted 60 from both sides, we just divide by 9, and we get negative 6 is equal to dh dt. Now we've done the math, and now we have to interpret this. What does this mean? Well, it means that if r was changing at a rate of 2 centimeters per second, and the volume was changing at a rate of 6 pi centimeters cubed per second, and the radius was 3 and the height was 5, it means that in order for all of these things to be true, the height, h, had to be changing at negative 6 centimeters per second. It means that the height is decreasing. So we'll go ahead and write that. The height is decreasing at a rate of 6 centimeters per second. And that's it. So this is a very standard related rates problem. For all related rates problems, what we do is we take an equation that we have that relates the quantities involved in the problem, and we realize that this is not good enough. We need some rates of change, and so we take the derivative of both sides with respect to time usually, And when you take the derivative of both sides, you have this new equation that has rates of change in it, and you can just put all of the necessary information in and solve for anything you don't have. And this will tell you everything you need to know. So, great. This is really all there is to it. If you have any questions, feel free to contact me during office hours or ask me in class. I'm happy to help. And as always, happy mathing.